Section 7.3 is titled Non-Terminating Decimals, and perhaps not the absolute best title for the section because it only includes one type of non-terminating decimals. But to start with, let's talk about what terminating decimals were. We did that back in section 1. So when did we say that a fraction could be written as a terminating decimal? What was our conditions upon which that would happen in the homework you just did?
2 and 5.
2 and 5. Okay, so it was when the reduced fraction, right? The simplified fraction. Okay, so what is it about 2's and 5's as it relates to a reduced fraction? What are we looking for? The factors of the denominator. So when the reduced fraction has only factors of 2 and or 5 in the denominator. So that was when we actually had the ability to say something was terminating. Is when we had a reduced fraction and the factors in the denominator were only 2's, 5's, or some combination of 2's and 5's. So what in the world would we do if a fraction, so we're working with rational numbers again, a fraction can't be written as a terminating decimal? So if the fraction was an integer over an integer, okay, so some number over some other number, and then the non-terminating, and it was non-terminating, then the issue is that it actually means it's repeating. So it would have something like a 3 or a 7 or an 11 or something like that as a factor of the denominator. That's what would have to happen in order for us to have a non-terminating, and what we're going to mean by non-terminating is repeating decimal. Okay, factors of something other than 2's and 5's. So for example, here's the number 1 over 24. If we were working with this problem in section 1, the question would have been something like, is it terminating, right? And you would have decided that it was not terminating because the denominator factors how? Has a 3, and what else does it have? It has 3 2's, because 3 2's is what you get when you have 8, right? So this is definitely not terminating. So let me show you what happens and remind you more than anything what happens if you try to do the division. That is, if you try to divide 24 into the number 1. And as with any decimal division or fraction division into turning it into a decimal, we're going to need to write some zeros in the placeholders here. Okay, so obviously 24 doesn't go into 1 and it doesn't go into 10. But it does go into 100 if we think about the three of these digits that are underneath the division sign. So how many times does 24 go into 100? 4 times, right? 4 times 24, what's that? I think it's 96. Yeah? Maybe that's what you guys are saying. It sounded like 86. 96. What's 100 minus 96? 4. So it doesn't go into 4. And it doesn't go into 40, so I'm going to put a 0 right here. Oh, I'm sorry, 40, not 20. I was thinking 20. Oh, it's been one of those days. All right, 40. How many times does it go into 40? Once. There we go. Now 40 minus 24. 16. It doesn't go into 16, though, right? Okay, so we're going to bring a 0 down. How about 160? Is it 6? That looks good. 6. It's not a good 6. Let's try again. 6. How about a 6 times 24? 154? 44? Okay. What do I get when I subtract 160 minus 144? 16? Alrighty. If I pull another 0 down, then I have another 160 here, correct? Just like I had the step before. Which means that when I do the division, I'm going to get another 6. And when I multiply by 6, I'm going to get another 144. Which means that from here on out, I'm going to keep getting that remainder of 16 over and over again, right? So I'm going to get 6's all the way across here. Here's my decimal point. I didn't write in my zeros. Let me do that. Well, we're not going to write that, of course, out because we can't write the number out forever. So above the first and only 6 that I will write, we're going to write a repeating bar. Just one of them, because that single number is what's repeating itself over and over again. We call this type of decimal a repeating decimal. And the repeating block of digits is called the repeat end. And there's a wonderful friendly note at the bottom. Expect to see your division when you convert these. Just like I expect to see your division in section 1 when you change it into decimals, because fully confident your calculator can do it. That wasn't the question, okay? I want to see that you can do it. My daughter will still tell you to this day that calculators are cheating. She does that because she's young, right? Because in school you don't use a lot of calculators in elementary school because there are certain things that we think you should be able to do by hand. So this is one of those things that you would be teaching at an elementary school level, so I want to see you be able to do it by hand so you can show your students, if you're teaching this, how to do it by hand. All right. Let's take a look at another example of this. The number is 29 over 99. Now, some of you know a shortcut on how to do this. That's not the point yet. I promise we'll get to the shortcut part of this idea in a minute. But we're going to do this just like we did in the last problem. The 99 is going to divide into the 29. Of course, it does not go into 29, so I need the decimal point there and a 0 so that I can take a look and think about this as the number 290. So how many times does 99 go into 290? Twice. That is correct. What is 2 times 99? It is 198. And if I subtract 290 minus 198, what do I get? More, because I'm not, it's not, yeah, it's not, we will get a 2. What else will we get in front of the 2? A 9? Is that right? 920? Okay, so the 92, which is less than 99, and then I'll pull down my next 0. How many times will 99 go into 920? It's 9. What's 9 times 99? 891. 920 minus 891. $29. And I contend that we can stop here. Now, if you don't see why we can stop here, I'm going to show you one more step further to verify this in a minute. But why, for those of you who do see it, why do you think I'm telling you can stop here? Because why? We're starting over where? At the beginning on this one. You don't always have to start over at the beginning, but this one does. 29 is where I started with here. So I've got a repeating value that I'm trying to do the division by. In particular, if I weren't so sure, if I didn't recognize it right off, we could do it another step, and we could take 290, and we could do the thing again, and we can recognize when I do 290, I get a 2. And you might be saying, well, wait a minute, I already did that. I already had a 2, and sure enough, and then when I get the subtraction for this, I get another 92, and if I bring down my 0 and I get a 9 here, I get another 891, and it's going to keep going back and forth. So if you aren't sure if you've found the right place, or if you aren't sure which of the decimals are the repeating part, if you go a couple more steps, you'll know for sure. If you're pretty comfortable with the idea, and you recognize at this point, right here, that this is where it starts repeating itself, then you don't need to do the rest of this. You have to recognize, though, then, that it's the 29, both of those numbers combined together, that are repeating. Not just the 2 and not just the 9. So the bar goes over 29. Now some of you might have recognized that at the beginning because this special denominator is a denominator of 99. And so that actually happens anytime you have all 9s as your denominator. It just becomes the number you had before the bar on top. So for instance, if you had 6 over 9, this is 6 repeating. And there's only one of them because it's only over 1 9. If you had 320, or let's say 32 over 99, then this would be 32. And both the 30 and the 2 would repeat because it's over the 99, 2 repeatings. So that's actually what's going on in the pattern. Now, in general, we're not going to be dividing every time by 99, so that's not a generally useful piece of information. But it's a specifically useful piece when you do notice it. All right, what I want to do next is I want to show you how we go in reverse. Okay? All right, so this is the number 61 hundredths, but it's repeating. Right, so if I were to think about what this number actually looks like, it looks like this. Right? 61, 61, 61, 61 forever. Agreed? So I want to turn that back into a fraction, and the problem is that with terminating decimals, all you have to do is you have to figure out what decimal place it stops at, and then you write that division by a power of 10. Well, this doesn't stop. I mean, in that lies the problem. That's exactly what the problem is it doesn't stop and give you a closed way to write it over a power of 10. So what are we going to do? Well, it's going to look a little bit like algebra. So here's what we're going to do. I want you to start by telling me that the n that we're working with, or the 0.61 we're working with, is equal to the value of n. Okay? That's all you're doing. You're just saying, I'm going to give it another name. The name I'm going to give is n. Okay? The next thing you're going to do is you're going to count how many decimals repeat. So what is the number of repeating decimals here? 2. Whatever that number is, you're going to multiply by a power of 10 to that, or you're going to multiply by 10 to that power. So this is the power of 2, so that means we're going to multiply by 10 squared. Also known as the number, what? 100. So this is 100 that we're multiplying by. So right here, we're talking about the number 100. Now, if I multiply 0.61616161 by 100, what am I going to get? You're exactly right. I'm not writing very cleanly, so let's try this again. So the 6 and the 1 that are multiplied by 100 come before the decimal place, right? Because it's multiplied by 100, it moves things 2 forward. But then all the other 6 ones are still here. Agreed? Now I don't really want to write out 6, 1 a whole bunch of times again, so I can write the repeating bar instead. But it's over here now, because the repeating bars still have to occur after the decimal point, so I can't put the repeating bar before. It's not, notationally that's improper. Okay, so is everybody good with that step? All we did is we found a power of 10, and we multiplied by it on both sides. The next step's the one that looks a little funny. And this will give justification for why I said what I did on the previous slide. We are going to subtract n from the left-hand side. What numerical value does n represent? What number? It's 0.61 repeating. So on the left, I'm going to subtract n. Oops. On the right, I'm going to subtract 0.61 repeating because these two values are equal. I'm going to subtract n from the left because the left side has n's on it. I'm going to subtract 0.61 repeating from the right because the right-hand side has 61 repeatings on it. But I'm allowed to do that because they represent the same thing. They look different, but they're the same. What's 100n minus n? 99n. And lo and behold, can somebody tell me what they see happening on the right-hand side? There is no more repeating decimal. That 0.61 repeating lines up perfectly. It's 616161 forever on both of those decimal expansions, which means that this part goes away. And all I'm left with is 61 as a whole number. That's nice. The goal is to figure out what n equals. So what are we going to do next? We're going to divide by 99. N is equal to 61 over 99. And if this has the ability to simplify, we would do so at this point. This one doesn't, because 99 is divisible by 3 and 11, and 61 is not. So we're stopped. Okay, so that looks sort of clean. I mean, like, you looked at this and you said 2 repeating decimals. I have 2 decimals, so I multiplied by 100. What's different about this question?
It's only one repeating.
Yeah, the only thing that repeats is the number 1. So like if I were to write this out in decimal form, it would look like this. Correct? That changes things a little bit. So let's start the same way because it doesn't change how we start. I have n equal to 6, 1 with the 1 repeating. Okay? Here's where it's important that you're counting the right thing. I have students who do this wrong every semester. What was I counting over here to decide what I multiplied by? The repeating numbers, not how many decimals I have, right? How many of the decimals repeat? 1. In this problem, I have 1 repeat. So 1 repeating decimal value. Which means instead of multiplying by 100, like I did in the last one, all I'm going to multiply by is 10. Okay? Just the power of 10. So I'll do the easy side, 10n on the left. What in the world's going to happen on the right? Yeah, I mean, really what I'm going to get is 6.1 repeating, but that's not an especially helpful way to write it. Okay, I'll show you why as we do our next step. This is correct, it's just not especially helpful to see it this way. Now the next step, what was the next step on your previous slide? What did we do next? We subtracted n, and we're going to do the same thing here. We're going to subtract n from the left, and we're going to subtract the value that n holds on the right. What's the value of n? 0.61 with the 1 repeating, right? So here's the problem. Whoops, I did that again.
You're at 1.
Well, that was fun. Let's try it again. Thank you. What's the problem? The problem is they don't line up. Do you see the 1 bars? They don't line up the way that it's written. Agreed? So coming back up here, what I'm going to do is I'm going to write this line of it a little differently. Instead of writing 6, 1 with the 1 repeating, I'm going to write it like this. Do you agree that that's the same thing? I've just sort of written an extra 1 in there, which is an awkward way to write it if that's what I was actually meaning. But for the purposes of wanting this to line up, that's a very helpful way to see it written. So what's going to cancel out then is this piece right here, agreed? Which is the repeating part that is the part we want to go away. So on the left-hand side, I have the 9n. On the right-hand side, I'm not going to have a whole number. It's okay, we'll fix that in a minute. Right now I've got 6.1 minus 0.6. So no whole number, but it still terminates, yeah? No repeating part. So what is 6.1 minus 0.6? It is 5.5. What's the next step? We'll do that in a minute. You're ahead of me, Allison, yeah. What would the next step be in general? Divide by 9, yeah. Now, in general, we're really done. The problem, the reason that we're not done, so to speak, is because we didn't quite finish the directions as they were given. The directions say that they want it in the form of a over b, where a and b are what? Integers. And 5.5, not an integer. So we're going to do exactly what Allison suggested, which is we need to get that 5.5 to become an integer. So we're going to multiply by 10. But if I do that to the numerator, I have to do it to the denominator. That's going to allow me to move my decimal place over. So this now gives me 55 over 90. And I'm still not quite done. Why? Yeah, it's not simplified now. So what could they both divide by? 5 would work. So I get 11 on top. What's 90 divided by 5? 18. Excellent. So 11 over 18 is the expression. Now think with me. Oh, yes, go ahead, Tristan.
Why did you multiply by 10?
Okay, so I'm going to let somebody else answer it. Somebody who caught that part. Why did I multiply by 10?
Because
That's okay. Go ahead.
because it can't be 5.5. That's not an integer. There can't be a decimal in the fraction.
Okay, so that's the reason of why I wanted to do something, right? I wanted to multiply by something to get rid of it. Why 10? Why did 10 work? Which I think was, yeah, multiplying by 10 or 100 just moves decimal places. So 10's a nice number to multiply by because it's going to move the decimal point one place. Very good. Good job, guys. How could I check my answer if I wanted to?
11 divided by 8.
Yeah, and you could use your calculator if you really wanted to, right? Yeah. There is absolutely no reason to use the back of the book on this problems, which, for better or worse, makes that really nice because it means you can always see whether or not you did the problem right. You just grab your calculator. 11 divided by 18. Somebody check for us. Is it 0.61 with only the one repeating? Oh, good. Then we did it right. Okay, any questions on the process here? All right. Let's see what's next. All right, let's do another one. Example 5. Oh, you know what? Let me do one more example that's not in here because it was something that was brought up when you guys were asking questions a moment ago. A moment ago, when we were doing questions from the last section, and you were trying to find out, is there a biggest terminating decimal less than 1? Do you remember that? One of the things that came up is this idea of what 0.9 repeating is. I want to do the same process with 0.9 repeating that I just did on the last examples, okay? So we're going to consider this number, and we're going to start out with that equal to n, just like we've been doing on all the other problems, okay? So how many decimals are repeating? 1, which means that I'm going to multiply this by the number 10. Excellent. So multiply by 10 on both sides. So this becomes 10n on the left, and it becomes 9.9 repeating on the right. Does that look okay? Okay, great. And then the next step is to subtract n from the left. What does n represent as a number? 0.9 repeating. So I'm going to subtract 0.9 repeating from the right. What am I left with on the left? 9n. What am I left with on the right? 9. Now what? What does 0.9 repeating equal? 1. And now you can blow your friends' minds when you go have dinner tonight. 0.9 repeating is not less than 1. It's exactly equal to the number 1. That's a crazy math fact. There's several crazy math facts. That's your crazy math fact for the day. Okay? Let's use that fact on this problem that we're going to do, though, too. This one actually has 0.9 repeating as a value in here, which means I really have the value of 1, right? So this one says to find any decimal between 1 and 1.1. So, between 1 and 1.1. What could we do to find a decimal between them? There's lots of decimals, but what could you do? Add them together and divide by 2, which will actually do part B. So let me do part B since you've moved to that point. Okay, so we could add them together and divide by 2. So what do you get when you add those together? 2.1. And what is 2.1 divided by 2? 1.05. Now, I actually think that this one works really well to think about in terms of money. So if I were to do this, which I think is where Allie was thinking to start with, because you talked about putting zeros on things. If you think about this as $1 and $1.10, what's some other number that's halfway between? Well, we already did $1.05 because we have that one on the bottom. Another one, $1.06 or $1.09 or $1.02. There's lots of things. And I'm just using money as an example because kind of my mind thinks in terms of money a lot. But there's nothing special. I mean, we could go like this as well, right? You know, just extra zeros and then some other number on the end would be just fine as well. So what if we did have something that wasn't so nice and clean, it wasn't 0.9 repeating, it was something else repeating? So let me just make up another example here because this one sort of looks a little bit weird because we didn't really do anything with the fact that there was the repeating except to recognize it was equal to something else, right? So let's say, for instance, that I had 0.54 repeating, and I had 0.55. Okay, so one terminates, the other one doesn't. You guys with me? So there's several things we could do. We could do kind of what we did on Part B, which is add them together, divide by 2 kind of deal. That would be one way to do that. If we added them together and divided by 2, you might think, but how would I do that? I've got a repeating business. Well, you know, we just write out a few of them. Okay? You don't even really need to write out very many of them. And you could take the 5 then, the other value. Your calculator works just fine to add those together and to divide by 2. The point of this problem is not can you add the decimals together. That was back in 7.2. Okay? So grab those two values, add them together, divide by 2. What do you get?
547.
So think with me for a moment. 0.547, is that number bigger than 54 repeating? Yep, definitely, because 54 repeating is 5454, and this is 547. So 547 is bigger than 545. Is it smaller than 55? Yes. So this would be an example of one such number that would classify or categorize itself as being between the two. Does that make sense? Okay.